Good evening, class 10. We continue with chapter 8 and the lesson 3. Last time we were talking about this particular law, Ohm's law, which stated that current flowing through a conductor or a wire is directly proportional to the potential difference applied across the ends of the wire. For example, if this is a wire and the ends are A and B, then the current which flows here, current I, is proportional to the potential difference applied across the ends of the conductor. How is potential difference applied? I had told you earlier, by applying by joining with a cell or a battery. This will send a current and the potential difference is provided by the battery. And this is the law which then says that V upon I is equal to a constant. And this particular constant was called the resistance R of that wire, and it is measured in these units. Unit of ohm with a small letter O, represented by the Greek letter, the last Greek letter omega. Then we talk about, for today, from here we can conclude that V is equal to IR. This is a very, very famous relation coming out of the Ohm's law. Very useful. Whenever we talk about electricity, this has to come somehow or the other. V is equal to IR. V is the potential difference. I is the current. R is the resistance. V is measured in volts, a volt. I measured in ampere. R measured in ohm. Now here, if I substitute, or maybe here, if I say V is equal to 1 volt, in that case, or maybe if I say current is equal to 1 ampere, in that case what will happen? V will become equal to R, or R will become equal to V, and here it gives a definition of resistance. Resistance is numerically equal to the potential difference applied across the ends of a wire. Potential difference applied across the ends of a wire, which gives a current of 1 ampere, or which sends a current of 1 ampere. Once again, resistance is defined as numerically equal to the potential difference applied across the ends of a wire so that it sends a current of 1 ampere through the wire. There it is. And also another thing, 1 ohm. How is 1 ohm defined? 1 ohm will be defined here. From here, check this out. R is equal to V upon I, means 1 volt upon 1 ampere. 1 ohm is equal to 1 volt upon 1 ampere. Or in other words, or in words actually, the resistance of a conductor is said to be 1 ohm. Resistance of a conductor is said to be 1 ohm if 1 ampere current flows through it when a potential difference of 1 volt is applied across the ends of the conductor. This definition which I've just spoken and another spoken little before that, both are given here on this page. This is page number 179. This I spoke a little earlier and this one I spoke just now. So you'll have to copy it from there while you're making your notes. And then coming to the next thing, if if the resistance is measured in ohms, then bigger resistances will be measured in kilo ohms, which will be equal to 10 raised to the power 3 ohm, or maybe mega ohms will be equal to 10 raised to the power 6 ohm. These are the bigger units, mega ohm and kilo ohm. And also something coming up as conductance. See, resistance, what does resistance do? Resistance makes the current flow with difficulty in the conductor. If a conductor has more resistance, means it will try and oppose the flow of current, and therefore the reverse of this will be called conductance. Reverse of resistance will be called conductance. Conductance means ease of flow of current, and this will be the reverse of resistance. The reverse of, or inverse, not reverse, the inverse of resistance is conductance. And this conductance has a unit also. The unit of R is ohm. Therefore, the unit of conductance will be inverse of ohm, or maybe like this. Earlier days, when we were students, when we were doing our graduation, we did not call it reverse of ohm, but we called it this. We called it mho. That means when you read it in the reverse order, it becomes ohm. But this is not used anymore. In place of that, they're using another word which is called this. Siemen. Siemens. Siemens is after the name of a German scientist. Actually, there were two brothers. One of them was an electrical engineer. Another one was also a big shot. So people do not know after whose name this was given. Siemens, and the letter used to present is capital S. Siemens is the unit of conductance, which is actually reverse of or inverse of resistance. Now the next thing is this. Coming up is this. It all looks very haywire, but this is exactly how it has been given in your book. So, please bear with me. All this irregularity which seems to be there, since when I say Ohm's law says V is proportional to I, or I is proportional to V, current flowing through a conductor is directly proportional to the potential difference applied across the ends of the conductor. If you plot a graph of I versus potential difference, that means in a circuit, if you have means of measuring current and means of measuring voltage, and if you have current here in amperes and you have potential difference here in volts, then because they are proportional to each other, directly proportional to each other, means if one is double, the other one is also double. If one is half, the other one is also halved, and so on. That means what you are going to get is a straight line like this. A graph will be a straight line, and obviously passing through the origin. It has to pass through the origin. Has to pass through the origin, because when potential difference is zero, no current will flow. So that is why it has to pass through the origin. And if you want to take a slope of this graph, slope means any triangle made, if this is delta I, and this is delta V. Sorry, delta V will be this side. Delta V means if this is V2 and this is V1. Similarly, if this is I2 and this is I1, then delta V would mean V2 minus V1, the difference of these two values. Similarly, delta I would mean I2 minus I1. Then this slope delta V upon delta I will be 1 upon the resistance. 1 divided by resistance, and we have talked about this. What is 1 upon resistance mean? 1 upon V, because V is equal to, let me think, V is equal to I, R is equal to V upon I. Yeah, 1 upon R, and that is what we have talked about already. So the slope of this curve gives you directly the conductance of that wire. If you draw it otherwise, if you draw the graph this way, you take potential here, potential difference here, and I here, then also you get a straight line. In that case, the slope will be Vi or delta I upon the delta V. In that case, this slope will give you resistance. It is just the reverse of that. You have to remember this conductance. You have to remember resistance measured in ohms, conductance measured in Siemens. I'm getting rid of this now. Next coming up is this. Limitations of the Ohm's law. That means Ohm's law, which we've been talking so far, has its limitations. And there is only one limitation, and that is this: temperature. When we are performing an experiment, must remain constant. That means the temperature should not be changing. If you are performing an experiment to prove the Ohm's correctness of the Ohm's law, the temperature of the wire on which you are conducting the experiment must not change. Normally it happens when a current flows through a conductor, its temperature starts rising, isn't it? So how to do that? That means we have to take a reading, one set of reading, then switch it off, wait for some time, take the next reading, again switch it off. That means you have to take several set of readings one by one, giving enough time for the wire to cool down if the temperature has risen. So the Ohm's law can now be said like this. Ohm's law can be said like this, that the current flowing through a conductor is directly proportional to the potential difference applied across the ends of the conductor, provided this sentence has to, provided the temperature remains constant. Provided the temperature remains constant. How many minutes?
14.
10 minute करीब और कर लेता हूँ. That is the only limitation. Please remember that. So when you write the Ohm's law, you have to write the limitation as well as. And then comes something else. What is that then? Something called these. They will sound very funny. Ohmic and non-ohmic resistances or substances. Any wire which follows, or any metal or anything that follows the Ohm's law strictly, is called a ohmic resistance, which follows the Ohm's law. And something which does not follow the Ohm's law is called non-ohmic resistance. That means if you draw a graph, which we had done little earlier, between I and V, it must be a straight line. This is for a ohmic resistance. For a non-ohmic resistance, same graph, when drawn, I versus V, will not be a straight line, it will be a curve like this. Also, another thing, I had told you earlier that ohmic resistance, the graph must pass through the origin. But here, it may or may not fall through the origin. It may be like this only, or it could be like this. It may or may not go through the origin. That is the difference. So, in a non-ohmic substance, the graph of V versus I or I versus V is a curved line. In an ohmic resistance, the graph of current versus potential difference is a straight line passing through the origin. May or may not pass through the origin, will pass through the origin, and therefore, similarly, you have been given differences between ohmic and non-ohmic resistances on this page here. Check this out. This is page 181. Here is the differences between ohmic and non-ohmic resistances. This is for you to learn. So please practice these. Learn and practice these. In fact, you should be making your notes now. With the help of this video, with the help of your book, you can make out the important notes. Everything important which is coming up here can be written as notes. And after this, time, Geeta ma'am?
18 minutes.
Quickly, I will go through this. It's not much, because you got to read your book also after the topic is covered in the video. Then there are factors which affect the resistance of a conductor. What are the factors that affect or that govern affecting the resistance of a conductor or resistance of a wire? There are they 4 of them. Number 1 is the material of the conductor itself, material of the wire, because some metals have very little resistance to offer, like metals. Current can easily pass through them. Then there are metals or other materials or alloys through which the current does not pass so easily, but passes. But then there are materials through which the current doesn't pass at all, almost doesn't pass. So depending from material to material, the resistance will be different. So this will affect. Number 2 is the length of the wire. The longer the wire, more will be resistance. That means I can safely write R is proportional to the length. Number 3, the thickness or the area of cross section. You see, there is a wire here, a piece of wire which is cylindrical, I'm assuming it's a cylindrical wire. Then the area, this area of cross section or the thickness. The thicker the wire is, or the thinner the wire is, more resistance is going to offer. That means R is inversely proportional to the area of cross section. Area of cross section. So you can write R, area of cross section, or if it is a cylindrical wire, 1 upon pi r square, because you know this area of a base of a cylinder is pi r square, that you know already from geometry. There it is. Number 4, what it depends upon. What we have left, it depends upon the temperature. Yes. The greater the temperature, the greater the resistance. Why it so happens? When the temperature rises, the motion of the electrons becomes more vigorous. They start moving even faster and to a greater extent. Too much of motion is there. In fact, commotion is there. And then there are chances that they are going to hit the positive ions also. And therefore, the resistance will increase. The current will be passing with greater difficulty now, because of the number of collisions will increase. So, in a short, after having done this, we have to come to a conclusion now, and that conclusion comes right here. If you join these two things here, resistance is directly proportional to the length and inversely proportional to the area of cross section. And if you want to remove this sign of proportionality, what do we have to do then? You have to multiply this side by a constant, so that this proportionality sign becomes equality sign, and thus constant here is this. You have heard about this. This is rho. Normally we used rho for density, but here we are using rho for another constant, which I'm going to name in a little while, but then let me complete this first. L upon A. A is the area of cross section. In case of cylindrical, it will be like this. So this rho is called this specific resistivity, the specific resistance, or just resistivity, or resistivity, just the specific, it's not just the resistivity. And from here, what you conclude now, finally, I'm going to bring this to an end now. Here, if you substitute things like this, if I put length is equal to 1 meter, area of cross section also 1 meter square, and then what happens? This is 1, this is 1. Sigma equals to become, rho becomes equal to R, and from here you can define this specific resistance or resistivity. How will we define? Specific resistance of a wire is equal to its resistance of a wire made up of 1 meter length and having a cross section area 1 meter square. A wire of having a length of 1 meter and the area of cross section 1 meter square. The resistance of this particular piece of wire is called the specific resistance, and obviously it will have the same unit as R, that is ohm. Time, ma'am?
25 minutes.
I think I'm going to stop it here. Or maybe just one more item I have to introduce. One more item to cause more confusion. I'm so sorry for that, but it's not confusion, but you have to learn all these things. There's another factor, conductivity or conductivity. You already know conductivity would means ease of flowing of current. Resistance is opposite of flowing current. It opposes the current. Conductivity will be the reverse of that. That means conductivity, therefore, this word conductivity or this term conductivity is represented by this letter, which is sigma. Small letter sigma, capital letter sigma is written like this. You know that in mathematics you must have done it. But then this is small sigma. This is equal to the inverse of what? Inverse of this. Specific conductivity. And then, since this is the inverse of this and this is measured in ohms, I told you something else also. Reverse of this, if this is measured in ohms, the reverse will be measured in this. And this is what I told you. This is nowadays what it is called as this. Siemens represented by capital S. So conductivity is equal to inverse of what is that there? Specific resistance or resistivity. That means bigger the value of sigma, better is a conductor. Smaller the value of sigma, more difficult it is. That means good conductors have a high value of this. Bad conductors or non-conductors have very low value for this. This is where I am today, and then we'll be moving on to the next topic next time when we meet. Until we meet again, I wish you all the best and God bless you. Reminding you that very soon we'll be collecting your practical files. I have asked for some practical files of the last years. We will see how much we can help you out. Thank you. Have a good time and good night, and God bless you.